Since the beginning of human civilization, mankind has wondered how traits are inherited from the parents to their children, why certain traits are more common in one family than another, and how to amplify useful traits in cultivated crops and domesticated animals. A Babylonian tablet more than 6,000 years old shows pedigrees of horses and their inherited traits. Hippocrates, better known as the father of medicine, suggested that parents give off invisible seeds, which would combine in the mother's womb to form a baby. The mechanisms of heredity, however, mostly remained a mystery until the 19th century, where Gregor Mendel comes in. Let's look at his background. He was born on July 20th, 1822, Heisendorf, Silesia, Austrian Empire, or current Czech Republic. From the beginning, Mendel was a smart kid, which sparked the priest's interest in him and advised his parents to send him to school. Mendel strived throughout his academic life, but later became a monk against his parents' will. As a monk, he entered the Faculty of Philosophy, which was headed by Johann Karl Nessler, who conducted extensive research about hereditary traits of plants and animals. From there, he wrote his famous
Versuche über Pflanzenhybriden,
or Hybridization in the Plant Kingdom, which reported his findings on the pea experiment. He doesn't take all the credit, though, and mentions others' work such as Kohlreuter Gartner's The Production of Hybrids in Vegetable Kingdom and how it contributed to his findings, which says a lot about his personality. He also mentions the sacrifice and hardships that those other scientists would have gone through for him to get the results he had.
I've always wondered, actually, how come Mendel chose pea plants?
I mean, there's a lot of reasons. Since pea plants in particular have their stamen inside the bud, foreign pollen can't easily reach the plants. This means that the experiment is easily controllable for Mendel, in which plants get pollinated by peeling the keel, which is like a protective blanket from foreign pollen, making it possible to transfer specific pollen that contain particular traits to another plant. Also, pea plants take a really short time to grow and display their traits compared to other plants, like about 60 days, and he worked on this experiment for 8 years. So imagine how much data he was able to get from that short amount of time.
He looked at plants for 8 years. How do you not mess up your data?
Well, another reason he chose pea plants is that their dominant and recessive traits are very distinguishable and consistent. This means that it'll make your life easier when you look at the same plant for 8 years. On the topic of his experiment, let's go more in depth on the traits of the plants. Mendel looked into 7 different traits: the shape of the seed, which were either round or wrinkled, the color of the seed, which was either yellow or green, the color of the flowers, which were white or purple, the shape of the ripe pods, which were inflated or deeply constricted, the color of the ripe pods, which were green or yellow, the position of the flowers, which were either axial or terminal, and the length of the stem, which were either tall or short.
Whoa, that's a lot.
So, Mendel started his experiment by interbreeding plants with different characteristics of the traits. For example, Mendel crossed a pea plant with round seeds with a plant with wrinkled seeds. What do you think happened?
All the offsprings were round, right?
Yep, all of the traits that were interbred only resulted in one type of trait. It was also the same when he interbred all of the other traits, like when he interbred plants with white and violet flowers. The results were all violet flowers. He was surprised with the results because he expected the offspring to have a mix of both traits, like a lighter purple when the white flower pea plant and the violet pea plant were bred. However, when all of the offspring showed to be one trait among those that were interbred, he was able to find that traits differentiated into dominant and recessive traits. Dominant traits masked recessive traits, making the offspring only look like the dominant trait, which in this case was purple flowers.
Oh, so the dominant side usually determined the flower color.
Yep, and this also happened with the other traits when he crossed a plant with one form of the trait with another. They all came out looking like their dominant trait, which is a trait that overpowers the recessive trait. A dominant trait is represented by 2 big A's, while the recessive is represented by 2 little a's. So for example, a plant only has one trait that can be physically seen. This is because when he mixed the homozygous dominant and homozygous recessive plants, they all got one dominant and one recessive allele, making them heterozygous.
I already knew that.
Good! You're so smart, but back then, Mendel didn't have the Punnett squares to work with. He didn't know about the alleles we know about today. Now Mendel was curious. Are the hybrids just like their dominant parent? What would happen if the hybrids were self-pollinated? I mean, previously every offspring showed dominant traits. Would it be the same? Would they share their traits? When the hybrids are self-pollinated, most of the offspring had violet flowers, but to Mendel's surprise, there were some that were white flowers. This shows that there are dominant and recessive traits of characteristics, usually in a 3-to-1 ratio. Well, to be more exact, there were fluctuations of the ratio between each trait, where sometimes the dominant trait would be a 3.1-to-1 or a 2.9-to-1. Mendel didn't stop with the first generations from the hybrids. He went to the second generation. He got the offsprings that showed dominant traits from the first generation and self-pollinated them, which is essentially when the pollen from the single plant is bred with itself by putting it in its own stamen. After finding the results of this experiment, Mendel realized that one of the dominant offsprings would always only give plants with dominant traits, while the other two had a 3-to-1 ratio of dominant to recessive traits. Let's look at an example. A pea plant from the first generation would give us 1 dominant purple flower, 2 heterozygous purple flowers, and 1 recessive white flower. If you self-pollinated the dominant purple flower, you would only get dominant traits, a 4-to-0 ratio, because it's like a dominant plant breeding with another dominant plant. While the other two, it would be like breeding a heterozygous plant with another heterozygous plant, which would give you a 3-to-1 ratio. So, if you count the plants that only gave dominant traits to the plants that could also give recessive traits, it would be a 1-to-2 ratio.